Tier 8 adds a value-aligned perspective. Stacking decisions can create unfair service outcomes across customers, increase environmental harm, or impose uneven workload on workers. The ethical framework makes these impacts explicit and controllable, rather than hiding them inside purely efficiency-driven optimization. We identify stakeholder values such as fairness for shipping lines, safety and ergonomics for workers, emissions for the environment, and reliability for customers. These values become measurable criteria so decisions can be evaluated beyond simple efficiency. This diagram shows how efficiency metrics and ethical metrics combine in one evaluation layer. Instead of optimizing only for speed, we explicitly track fairness, environmental impact, and worker welfare. We compute a total score that combines efficiency, fairness, environmental impact, and safety. The key idea is transparency. The terminal can explain why a solution was selected, and stakeholders can challenge it if it violates agreed values. Fairness constraints prevent systematic disadvantage. For example, we can constrain service level variance between customers so one group is not consistently placed in hard-to-access positions. This turns fairness from an informal promise into an enforceable rule. This slide translates ethical requirements into implementable checks and penalties, such as constraints on discrimination risk, minimum safety thresholds, and environmental limits. The point is operational. Ethics must be implementable, auditable, and testable. Constitutional artificial intelligence means we define a set of non-negotiable values that cannot be violated, even if efficiency could be improved. This helps ensure that automated decisions remain aligned with terminal policies and stakeholder expectations. A concrete example illustrates a common trade-off. A purely efficiency-driven plan might slightly outperform alternatives, but it may systematically disadvantage smaller customers. By enforcing fairness constraints, the terminal can accept a small efficiency decrease of 3% to eliminate systematic disadvantage. The main value is transparency. Stakeholders can see the trade-off rather than having it hidden inside a black box. Practice writing a complete integer programming model for a small stacking instance. Define sets, parameters, decision variables, objective, and constraints. As you do this, focus on the blocking logic. Your model should explain exactly when a reshuffle is counted and why. Implement the priority-based heuristic and show a step-by-step placement process. Track how each placement changes future reshuffle risk. The goal is to build intuition for why greedy choices can help and why they can also fail. Design a genetic algorithm for stacking and demonstrate chromosome encoding and fitness evaluation on a small example. Then show how the best solution improves over a few generations and explain what kinds of placements the algorithm discovers. Formulate a reinforcement learning version of the problem and propose an ethical evaluation layer. Describe states, actions, rewards, and fairness constraints in plain language and explain what failure mode each design choice prevents. This slide compares the tiers across key metrics: reshuffles, computation time, deployment complexity, and adaptability. The goal is not to crown one winner. The goal is to choose the right method for the terminal's operational constraints. To summarize, stacking rules are a major lever for terminal efficiency. Tier 1 provides a rigorous baseline model. Tier 2 offers a fast operational heuristic. Tier 3 improves quality through global search. Tier 4 learns adaptive policies. Tier 8 ensures decisions remain aligned with fairness, safety, and environmental priorities.